In this set of notes, I'll be reviewing some basic concepts on chemical bonds. So the first question that we ask is, why do chemicals bond together at all? Why do atoms of different elements want to bond together? Well, the reason is all about stability. And in fact, you'll find that stability drives a lot of things in chemistry. Things want to become stable because, just naturally speaking, that's a more sustainable way to be. If you reach stability, that means that you're at a nice, comfortable place, and you'll want to stay there when you're stable. If things aren't stable, then they tend to react to become stable. And that's what we find that elements do when they form bonds. So as a little bit of a review from the last unit, stability is depending on the valence electrons. Everything wants to be like noble gases, which have full outer shells on their electrons. They have filled up energy levels because that's really, really stable. And so they try and fill up electrons until they get the correct number of valence electrons to be like a noble gas. As a bit of a review here, this is called the Octet Rule, and things want 8 valence electrons to be stable. Again, this is like the noble gases. Now there are 4 elements on the periodic table: helium, hydrogen, helium, lithium, and beryllium, where they only require 2 valence electrons. This is because in the first energy level, there are really only 2 spots for electrons, all right? There's only the S sublevel within the first energy level, and so things like hydrogen and helium only want 2 electrons in their outermost energy level, and then lithium and beryllium will lose electrons to become like helium as well. So those are also included in the ones that only need 2 valence electrons. Everything else wants 8 because the valence electrons tend to be the S and the P sublevels, and so generally speaking, everything else wants 8 valence electrons to become like the noble gases, which all have 8. These noble gases are all the ones that in that last column of the periodic table, and they're very stable and very unreactive. They include helium, neon, argon, krypton, xenon, and radon. Okay, so this is what's going to happen with these atoms as they're trying to become more stable. They're going to alter the number of electrons that they have, and they've got some different options here. They can gain electrons, they can lose them, or they can share them between other things. So we'll also talk about the different sorts of compounds that atoms form. Compounds, remember, compounds are pure substances, all right, which have atoms of different elements bound together. And to analyze this situation, we use something that's called a Lewis dot diagram, and I'll be explaining that here in just a moment. So these Lewis dot diagrams, what they are is they're a way of showing how the valence electrons organize themselves around an atom. And here are sort of the list of steps, or the explanation for how these diagrams work. So each dot represents a valence electron, all right? You're going to pretend that there's 4 little boxes, one on the top, one on the bottom, one on the left, one on the right, and each of these boxes holds 2 electrons in it, all right? And you're going to fill them up so that, kind of like the bus seat rule that we talked about when we talked about the different rules for orbitals and things like that. You don't want 2 electrons on any one side of the atom until every side has at least 1 electron in it. And I'll go through some examples and explain that, and hopefully that should make more sense. The other thing is here, the dots, there's no rule that says, fill the top first, or fill the bottom first, or fill the left or the right first. But you have to fill all of them with 1 electron before you start putting the second one in. So what that means is there are actually a variety of different diagrams that you can get depending on the substance, but I'll kind of explain that too as we go through. So we're going to do some examples here. So hydrogen, if you look on the periodic table, by the way, going along the rows, that allows you to know how many valence electrons something has. So actually, going along the columns, I should say. So the first column, which contains hydrogen, that entire column has 1 valence electron. It's group 1A for 1 valence electron. The group with beryllium in it, that's the second column, All of those have 2 valence electrons. If you jump across to boron, everything in boron's group has 3 valence electrons. Everything in carbon's group has 4 valence electrons. Everything in nitrogen's group has 5 valence electrons. Oxygen's group has 6. Fluorine's group has 7, which are the halogens, and then the noble gases all have 8. So if we find hydrogen, again, as I said, it has 1 valence electron. And so you just put 1 electron on one side of the hydrogen. Here it's put on the right side, but it could be on any side. It could be on the top, the bottom, the left, or the right. We just put it on the right in this case. Nitrogen, all right, nitrogen has 5 valence electrons, so we need to put 5 electrons on here. You could put this starting on any side, but you have to fill up each side here with 1 electron first, all right, and then now we have to put the 5th electron on, and it's going to double up on one of these sides. This 5th electron could be put on any of these sides now because they each have 1, and so we're ready to start doubling. We put it on the top here, but you could have put the 2nd electron on the left, the right, or the bottom. Calcium has 2 valence electrons, so we put 2 dots, 1 and 2. Now, here it's on the left and right sides of the calcium, but again, it could be on the top and right, or on the bottom and right, or on the top and left, or the bottom and left, or the top and bottom. Just as long as the 2 electrons are on different sides of the calcium, meaning that they're not both on the right, or not both on the left, or both on the top, or both on the bottom. As long as they're on different sides of the calcium, we're good here. So going through, carbon has 4. This one, you can start putting the electrons on any side, but by the end, you should have 1 electron on each side. So it should look like this. Chlorine has 7 valence electrons, so we fill it up. 1, 2, 3, 4. All right, so we filled up each side individually. Now we start doubling up. 1, 2, 3. All right, and since chlorine has 7 valence electrons, that's where we end up. Now again, the side with the single electron could be any of the sides. It's just arbitrary that in this case, the left side is the one that has just the single electron on it. But it could be, you know, it could have been any other way. Argon, we have 8 valence electrons on this one. So 1, 2, 3, 4, right? And then we start doubling them up. 1, 2, 3, 4. And you see you have 2 electrons on each side. So this one actually, this is the only way we could do it because it's all filled up. There's no place else to put electrons. So this is what argon's Lewis dot diagram looks like. All right, now continuing on here to talk about the bonding. Atoms combine to form these compounds by making chemical bonds. A basic idea in bonds is that there's actually not a physical object connecting the 2 atoms together. What's connecting them together is an attraction that they feel together, like an electrical sort of attraction. So it's a force that exists between the atoms that holds them together. It's not actually like a physical bond. When they come together, we use formulas to describe what sort of composition the different molecules or substances have. And what we have is, we have 2 different parts of this. We have the letters, which tell you what kind of element we have, and then we have the subscripts that tell you how many of that atom we have. So the symbols or the letters will tell us what kinds of atoms we have, and those subscripts tell us how many. So H2O means we've got 2 hydrogens, and then the O, since it has no subscript, implies that we have 1 oxygen there. It's just like an automatic subscript of 1 if it's not written. NaCl, that's 1 sodium and 1 chlorine. C2H5OH, this one's a little bit tricky. There's 2 carbons, and then there actually end up being 6 hydrogens. There's the 5 hydrogens listed there at the beginning, but then there's another hydrogen there at the end. The reason they write it this way is because this is a substance called ethanol, and alcohols often end with OH to show that they're alcohols. And so we have a total of 6 hydrogens, 5 at the beginning and then that 1 other one at the end. And then we have just 1 oxygen because it does not have a subscript on the oxygen. Al2 So4 is a little bit different here. That set of parentheses there with a subscript after it shows us that we double everything in the set of parentheses. So aluminum, there are 2 because aluminum has a subscript 2. But since we double everything in the set of parentheses, we have 2 sulfurs and then 8 oxygens because inside the parentheses it says 4 oxygens, but then we double it because there's a subscript outside of that set of parentheses, which doubles everything inside. So 2 aluminums, 2 sulfurs, 8 oxygens in that last one. So now I'm going to talk specifically about a type of bond that's called ionic bonding. And so this has to do with positively and negatively charged ions attracting one another. And this almost always occurs between a metal and a nonmetal. So try and remind yourself where the metals are on the periodic table and where the nonmetals are, because if a metal bonds with a nonmetal, typically speaking, it will make an ionic bond. When you have a substance that's made through this kind of bond, it's called an ionic compound. It's made up of positively charged and negatively charged ions. Remember, the positively charged ions are called cations, and the negatively charged ions are called anions. One property of these ionic substances is that they form these crystalline lattice structures, which if you look at them, what a crystalline lattice is it's a highly organized grid structure where the substance is very, very straight cut and organized into this, perfect little grid. And so we call these crystalline lattice structures. The result of that is that if you look at ionic compounds on the large scale, they make these really, really nice shapes. So what we have here is a picture of some crystals of sodium chloride, which are table salt, and you see that they have these really nice, boxy geometric shapes. This comes about because of the crystalline lattice structures that exist with the ionic compounds. As a second property here, they're brittle. Brittle is the opposite of malleable and ductile. So things that are brittle, if you try and modify their shape, they tend to just break and crumble. Things that are malleable, if you try to think malleable is like clay. So clay, if you tried to squeeze it in your hand, it would conform to the different shapes. If something's brittle and you squeeze it in your hand, it will just crush into powder and break apart. So ionic substances tend to be brittle. Continuing on here. A lot of them dissolve in water. Water is actually a really, really polar molecule, which we haven't got to talking about much, but polar means that it has a positively charged end and a negatively charged end. The oxygen is negatively charged, and so the oxygens are attracted to the sodiums in this example, or the cation part of the ion. The hydrogens are attracted to the negatively charged part of the ionic compound, and so in this case, with sodium chloride, we're talking about the chlorines, and they're attracted there. Something else is that water, if you have pure distilled water, it does not conduct electricity, but if you put an ionic substance in it, it will conduct electricity. So ionic substances tend to help water conduct electricity. And the ionic substances tend to have very, very high melting points. Something here is, to remember this, is if you think about salt, which is an ionic compound, and you put salt in a pan on your stove and you were to heat that salt, you could probably never get it to melt because salt has such a high melting temperature that you wouldn't be able to get it to melt. So you could sit there and heat the salt all day and it would stay as a solid and not melt. So I'm going to talk a little bit about how these ionic substances work. What we get is we get two things like sodium and chlorine coming together here. Chlorine, if you do its Lewis dot diagram, you get something that looks like this. Chlorine has 7 valence electrons. It wants one more to be a noble gas. If chlorine got one more valence electron, it would be like argon. Sodium wants to lose an electron so that it can be like neon. So what ends up happening in this case is that sodium gives its electron to chlorine, and then they're both happy. And then as a consequence, what happens here is the sodium becomes positive because it gave up an electron, and electrons are negatively charged. All right, and chlorine becomes negative because it took on an extra electron, and again, electrons are negatively charged, so taking on an extra electron makes you negative. So we've got Na plus and Cl minus in this case. And the thing that adds some extra stability to this is after this transfer occurs, sodium and chlorine are attracted to one another because opposite charges attract each other. So plus charges attract minus charges, and you get the little sodium atom now very, very attracted to the chlorine atom. This is just another representation of that same process with the Bohr model of the atom shown there. And you can see that the sodium transfers 1 electron out of its outermost energy level, and then when you look over at the other side, you can see that sodium has a filled first and second energy level. Chlorine, when it gains that electron, gains the last electron it needs to fill up its third energy level, and so they're both good because they both have filled energy levels and they have electron configurations that are similar to those of the noble gases. All right, now to talk about covalent bonding. So ionic, just to review, ionic was between a metal and a nonmetal, and it involved the transfer of an electron from one atom to another. Covalent bonding is a little bit different because this one is all about sharing the electron between atoms. And so it happens with two nonmetals, or sometimes more. That can be a large group. And what happens is they're going to share the electrons between them. Technically speaking, I think lots of you have heard the word molecule before. A molecule is used specifically to describe a covalent substance. You might hear me at some points misuse the word molecule, and feel free to correct me if I do, but if you're talking about an ionic substance, you should call it an ionic compound, not a molecule. So just a little bit of vocab there. Molecules are talking about covalent substances. The thing about these molecules is that they have a lot of different possible structures. They could have very small ones that just have two atoms in there, or they could have really extensive polymers like DNA or like proteins or things like that that have thousands of atoms all within one molecule. And because of that, they have a large diversity of different properties, so the molecules can have different shapes and sizes and physical and chemical properties. And because of that, there's not a clear set of properties that we give to covalent substances, because really they take on all sorts of properties. You know, there's some that are solids, some that are liquids, some that are gases. There are some that are polar, there are some that are nonpolar, there are some that are hard, there are some that are soft. And so we can't really make any big claims about the properties of covalent substances like we did about the properties of ionic substances, because covalent substances are so diverse. So to show you how this covalent bond works, I'm going to use the example of ammonia, which is NH3. So first I'm going to fill in the electrons on nitrogen. It has 5 valence electrons. All right, and then I'm going to bring in 3 hydrogens. These hydrogens each have 1 valence electron. What you see here then is that there are 3 areas here where they're sharing electrons. If you count the total number of electrons around nitrogen, you should get 8, which is good for nitrogen because nitrogen wants access to 8 electrons to complete its octet. The hydrogens, if you count the number of electrons around them, each hydrogen has 2 electrons, which actually is good for it because it wants to be like helium. And remember, it's one of those exceptional ones that only wants 2. And so everything's kind of good here. So the hydrogen and the nitrogens are sharing those electrons, but everybody ends up winning out because they all get to be like noble gases in the end. This is just summarizing that idea. Again, covalent bonds are all about sharing electrons, whereas ionic bonds are about transferring electrons, and it's a slightly different process here. So there's one little last step of review here. We're going to predict whether these compounds would form ionic or covalent bonds. H2O, hydrogen is a nonmetal, and oxygen is also a nonmetal. And so if you have 2 nonmetals, it's going to make a covalent bond. NaCl is sodium chloride. That's normal table salt. We've talked about a lot of that in terms of the fact that it's ionic, but as the rule of thumb says, we know it's ionic because sodium is a metal, chlorine is a nonmetal, and a metal and a nonmetal form an ionic bond. This next one, C2H5OH, that is covalent because they're all nonmetals. Carbon is a nonmetal, hydrogen is nonmetal, oxygen is a nonmetal, and hydrogen, again, that's that 6th hydrogen on there, that is a nonmetal as well. And so if they're all nonmetals, it's going to be covalent. And then this one here is a little bit different. It's got aluminum in it, which is a metal, and then it's got some nonmetals in there, so that clues us into the fact that it's going to be ionic. Also, this SO4 is a special kind of substance, which we'll talk about later on in this unit and in some other units in the future, but SO4 is actually called a polyatomic ion. It's sulfate, all right, and so polyatomic ions are covalent substances that are also charged, and so Al2 So4 has the aluminum metal in there, and it has that polyatomic ion in it, the SO4, and so what ends up happening here is that it's ionic overall. Okay, that was a lot, and it was pretty fast. Make sure that you understand these things, and as always, if you have any questions, come in and ask.